Hello everyone, welcome to the week 8 discussion session. Uh, Today we'll be looking into the various aspects of uh, uh, parasitics and the driver circuitries required for optimal delay and energy calculation of this parasitic wire parasitics. Okay, so let's start into it. So our first question is, Acha, I just want to confirm. Hope I'm audible, right? Okay, fine. So the first question is, find the propagation delay TPD for the signal propagating in wire A, neglecting the parasitics of the inverter and the wire's resistance. Okay, fine. So what are the various parameters that have been given to us? First of all, R effective is given as 1 kilo ohm. Okay, length L is given 1 millimeter. C adjacent is provided 120 femtofarad per micrometer. Okay, Ca is given 80 femtofarad per micrometer, and Cb is provided as 80 femtofarad per micrometer. Fine. So okay, fine. Now, as length of the wire is given as 1 millimeter, so the net Ca would be 80 femtofarad. If 1 micrometer length constitutes 80 femtofarad, then 1 millimeter would constitute a capacitance of 80 femtofarad by 10 to the power minus 6 into 10 to the power minus 3 farads. Correct? Which would be equals to Cb also. And let me write the net capacitance as Ca dash and Cb dash for distinguishing between these two. Okay. Therefore, it will come around plus 3, so 80 picofarad Ca prime equals to Cb prime. Okay. Now, propagation delay is the worst case delay. Like I've been telling you guys since long that there are two kinds of delays. One is the propagation delay, another is the contamination delay. Contamination delay is the best case delay or the least value of the delay, and propagation delay is the worst case delay or the highest value the delay can take on. So we know this aggressor circuit, this configuration can take three forms in total. First of is, this is my input in the aggressor and the output is floating. In that case, I have to charge the C adjacent circuit and I would get a net capacitance of Ca plus C adjacent, right? Second condition comes, output and this aggressor and this what it is called, this aggressor circuit and this victim circuit are the driver of this aggressor and victim circuits are seeing the same kind of input. In that case, I only need to charge the capacitance Ca, and this capacitance, as the voltage between these two nodes would be similar, voltage difference would be 0, so I don't need to charge this circuit. And the third condition would come when say the aggressor is changing the input, the driver of the aggressor is changing the input, and the driver of the victim is also changing its state, but they are opposite in direction. In that case, the capacitance of the C adjacent, the voltage across the C adjacent would be experience would be double. In that case, the capacitance that we will be experiencing would be Ca plus 2 into C adjacent. And you can see this would be my best case because it has the least capacitance, so I have to charge the least amount of capacitance, so it would be my contamination delay case. And as this one contains the highest amount of capacitance, it would take highest to charge this circuit in this configuration. The highest time would be required to charge the circuit in this configuration, and this would be my propagation delay. Okay, so now my propagation delay would be, T propagation delay would be how much? It would be R effective Rc, and C would be how much? It would be Ca, like I have written the Ca prime plus 2 into C adjacent. Fine. So how much it would come? It would come as uh, it is 1 kilo, 1 kilo ohm into Ca prime is coming as 80 picofarad, and 2 into C adjacent would come as 120 femtofarad per micrometer into 1 millimeter. Okay, so this would come as 10 to the power 3 into, so 80 picofarad. So 80 pico plus 2 into it would be how much? Plus 3, so 240 pico. So it will be 320 pico. So 10 to the power 3 into 320 pico. So it would come 320 into 10 to the power minus 9 second. Okay, or 0.32 microsecond. Correct? Now here the answer is given as nanosecond. It would not be nanosecond, it would be in microsecond. The answer given here is wrong. Okay, because if you follow the lectures, even the case study that sir is considered in his example, here also he is getting a result of 0.32 nanosecond, but the values that he has used, the orders were different, right? So like here also it is given as 0.32 nanosecond, but it would be actually the answer would be 0.32 microsecond will be the answer. Hope that's clear. Okay, okay, let's move forward. Okay, so question number 2, the crosstalk noise effect when the victim inverter is half the size of the aggressor inverter is roughly 25%. The second statement is the victim inverter is twice the size of the aggressor inverter is roughly 25%. The third statement is the victim inverter is equal to the size of the aggressor inverter, then the crosstalk noise effect will be roughly 17%. Let us look at them one by one, and let us start from this case. Okay, point number 3. Fine. So in case number 3, it has been mentioned that okay, first let us look into the expression of this crosstalk noise. We know del VB equals to del VA, okay, into C adjacent by C adjacent plus CB, okay, into 1 plus K. This is the expression that we get if resistor was not present, and if resistor was present, this 1 by 1 plus K term would come into the picture. So where K is equals to how much? K is equals to RA by RB into CA plus C adjacent divided by CB plus C adjacent. Correct? Okay. Now, in case 3, it has been mentioned that the victim inverter is equals to the size of the aggressor inverter. Okay. So their strengths have been given as equal. W1 is given as equals to W2. Fine. Now, if I consider this case, only this part, if I consider only this part, and if I consider that C adjacent and CB are equal, like this is the case even when this resistor was not considered, right? Then we would see that delta VB equals to delta VA by 2, that is 0.5 delta V equals to delta V. Okay, so considering that if that is the case that we are considering that the crosstalk noise, if resistor was not present, was around 50%. Okay, like the delta VB would be 50% of delta VA. That's why upon that condition we can also take this, that the RA, the aggressor would be, resistance would be twice of, like RA would be twice of RB. Okay, now delta VB would be delta VA. Okay, and I have considered C adjacent and CB to be equal, so 1 by 1 plus 1 into 1 by 1 plus K. Now as C adjacent and CB all are equal, I have considered the condition that C adjacent equals to CA equals to CB, so I will get only RA by RB. Okay, 2 1. So okay, so RA by RB, and if W1 equals to W2, I can see RA is twice of RB. So if RA equals to twice of RB, what will happen? It will be 1 by 1 plus 2. So delta V A by 2 into 1 by 1 plus 2. So delta VA by 6. Correct? It comes around 16.66%, which is near to 17%. Okay. So the third statement, that the victim inverter is equals to the size of the aggressor inverter, is roughly the crosstalk noise effect is roughly 17%, is true. Okay. Now let us look into this case, first case. Okay. It is given the victim inverter is half the size of the aggressor inverter. Okay. So if victim inverter is half the size of the aggressor inverter, then the victim inverter is half the size. Okay. So here my 2W1 would be equals to W2. Okay. Therefore here the relation between RA and RB would be twice RA would be equals to twice RB. Correct? Let me think on it for a minute. The victim inverter. Acha, the victim inverter is half the size of aggressor inverter. Yes. Okay. So W2 is the victim inverter. So if it is half the size of this, wait a minute. Yes, it's correct. So twice RA would be equals to twice RB. Therefore, my delta VB would be equals to delta VA. This would remain same, 1 plus 1, that is 2, and this would become 1 by 1 plus RA by RB. So it will be 1 by 1 by 1 by 1 plus 1. So it will become delta VA by 2 into 2, 4. So 2 into 2 is delta VA by 4 equals to 25%, right? So this is also true. The second statement is the victim inverter is twice the size of the aggressor inverter, is roughly 25%. Okay, let's look into it. Now it is saying the victim inverter is twice the size of aggressor inverter, is roughly 25%. So now my RA would be equals to 4 times RB, because if W1 equals to W2, RA was twice. So if W1 is twice to W2, RA would be 4 times RB, right? Therefore delta VB would come here as delta VA by 2, 1 by 1 plus RA by RB. So it would be RA by RB is 4. Okay, so it would become delta VA by 2 into 5, 10. Therefore delta VB is 10%. So here it is given as 25%, so it's false. Correct? Okay. So the crosstalk noise effect depends on the size, relative size, the ratio of the sizes of aggressor inverter and victim inverter, as you have seen. Okay, then let's move to the next question. Okay, question number 3. The question is, for a repeater what is the optimal inverter size W for optimal inverter size W for minimum delay given, switching resistance is given, capacitance of unit inverter given, and resistance of the wire and capacitance of the wire per unit length is also provided. Okay, fine. Now let us draw the this circuit, the RC model. Okay, fine. We have considered the repeaters are the repeater inverters are scaled by a size W, right? So its resistance would be R by W and its capacitance would be C by W. Sorry, C W, not C by W, C W, C into W. But as like we have seen that due to this technology note like folded technology and all, we can get another constant factor, that is rho inverter, whose value depend upon the layout of the circuit that we are working on. Okay, right. And there will be another capacitance. It is actually basically it will be coming from the pi model of the wire. Okay, so it will L by 2n, it will be RW L by n, it will again be CW by CWL by twice n. Okay, and finally final capacitance will be, it is valued on as how much it would be? It would be C into W. Okay, so basically this is my repeater 1, this is my repeater 2, and this is my okay, so this is my the pi model, the wire. Okay, fine. So by Elmore delay model we can find the propagation delay. By Elmore delay model, the propagation delay for one such segment would be how much? It would be R by W, this R by W, this R by W into this capacitor should come, this capacitor, all this capacitance should come into picture. So it would be R by W into first this capacitance, C into W into rho inverter, okay, plus this capacitance would come into picture, C by W into L, C not C by W, CW, that is capacitance of wire per unit length, okay, by twice of n plus CWL by twice of n due to this one, and plus C into W. Then effect of this resistance would also come into picture, this resistance also come into picture. So plus RW L by n, and which capacitance would come to picture here? By Elmore delay model, this one and this one. So into CW L by twice n plus C into W. Correct? Now this is for let me shrink it. Okay, fine. Now this propagation delay is for one segment. Now for n such segments, it would be the propagation delay for n segment. How much? simply, and n would be multiplied here, right? So nr by w c w row inverter plus 2n, so 2n by 1 by 2n plus 1 by 2n would be 1 by n, so cwl by n plus cw, sorry, c into w plus rwl. This n and n would cancel each other, and we'll get cwl by 2n plus c into w. Okay, now how to find the optimum n condition? Simply for, sorry, for optimum w, I will be taking partial derivative of this t propagation delay for n segment with respect to w, because I want it for optimum w, right? If I wanted for optimum n, I would have taken the partial derivative with respect to n. So how much it would come? It would come, so okay, so here w cancels, so it would be 0. Here w will be there, so it would be minus 1 by n square, something like this, right? So it would be r cw r into cw l and n cancel, divided by w square, right? Again w term will be there or not. Okay, plus cw, w again cancel, so again 0. Now this here also w term is not there, so again 0. Here w term is there, so it will be rw l into c. This is equals to 0. So this implies from here I can find the value of w. So w with minimum delay would be equals to r into cw by rw into c. Correct? This is the expression that I am getting. Okay. Okay, fine. Now using this expression, I know that the given values of r is 1 kilo, c is 20 femto, rw is 10 ohms per micrometer, and cw is 0.08 picofarad per micrometer. So r is 1 kilo, means 10 to the power 3. cw is 0.08 pico means 10 to the power minus 12 by micrometer. Okay, and rw is 10 ohm per micrometer, c is 20 femto, femto is 10 to the power minus 15. So micro will cancel, so what I will get is root under 0.08 10 to the power minus 12 plus 3 is minus 9, and here minus 15 into how much, divided by 2. So if I cut it, it will become 4, and so plus 15 due to this 15, and minus 2 for this 0 0, and for the minus 2. So how much I am getting? I am getting 4 into 10 to the power 15 minus 9, 11, 13. So 100 I am getting. So it is root under 400, which is equals to 20. So is 20 an answer? Yes, 20 is an answer. So my so we can see the optimal inverter size is, optimal inverter size W is how much? 20. Okay, hope that's clear. Anyone have any confusion? Take a moment and see you are understanding or not what I have done here. If it's clear, then we can move to the next part, next question. So the next question is, and again in the previous one also, now if we wanted to find that the optimized value of n, instead of taking here the partial derivative with respect to w, we could have simply taken it with respect to n, and from there we could have got the expression of n, and we could have found the value of the optimized number of stages of the number of repeaters that are required. Okay, fine. So the next question is, select the correct option. So the options given are: the profile energy per unit length of repeater circuit follows a parabolic profile. Option number 2 is, the profile of delay per unit length of a repeater circuit follows a linear profile with respect to W. Third one is, delay per unit length of a repeater circuit follows a parabolic profile. Or the fourth one is, the profile of energy per unit length of a repeater circuit follows a linear profile with respect to W. Okay, look into it. Sir has like in his lectures he has discussed how he has got it. We'll be looking into the curves, and I'll be also telling a short like an intuitive way to understand. Even if you don't remember which one is which, you can, from the expression also you can get the values, that which uh, like what should be the curve for the energy curve and all. Okay, what should be the trajectory, what should be the trajectory for the energy curve. By looking into the expression only you can tell. Let's look into it. Okay, so basically the curves for the propagation delay per unit length is given as something like this. It was a parabolic curve, right? Where this represents the minimum delay case. Okay, and say this one represents twice of W of minimum delay, and this represents W minimum delay by 2. Okay, and for energy it was energy per unit length, it was how much? It was something like a straight line. Let me draw it below. Energy per unit length. Okay, so it was something like this. Fine. So from here we can see that the value for which my W min is minimum is not the same uh, value of W for which my energy is minimum. Okay, so there is a kind of trade-off between them. So it depends on the application whether we want an energy optimized circuit or we want a delay optimized circuit. Okay, or there could be a third trade-off, like uh, I have to find a point where neither it is optimized completely for delay, neither it is completely optimized for energy. It is somewhere in between, and we can use other parameters such as an energy delay product to find that point. Okay, so you can see the profile of delay is a parabolic, and the profile for energy per unit length versus width is a straight line. So the conditions that are given, the first condition is the profile of energy per unit length, this one, of a repeater circuit follows a parabolic profile with respect to W. So no, it is false. It follows a linear profile. The second statement is the profile of delay per unit length of a repeater circuit follows a linear profile with respect to W. It doesn't follow a linear profile, it follows a parabolic profile, so it is also false. The third statement is the profile of delay per unit length of a repeater circuit follows a parabolic profile with respect to W. and it's correct, so true. And the fourth one is the profile of energy per unit length of a repeater circuit follows a linear profile with respect to W, and it follows a linear profile, so it is true. So the correct sequence is false, false, true, true. This is the answer. Okay. Now we, like, if you remember the expression of energy per unit length, it was what it was. Energy per unit length was something of this sort, C into W. Okay, 1 plus rho inverter, space is not there, let me write it somewhere else, right here. So energy per unit length was C into W, 1 plus rho inverter plus CW L by N, okay, VDD square by L by N. Okay, now for minimum delay, this should be, for minimum delay case, this should be minimum delay, this should be minimum delay, and this should be minimum delay, right? Now you can see here the variation of the W is simply from here expression only, you can see it is linear, linear with W. So if my W keeps on increasing, my energy, if my W keeps on increasing, my energy per unit length would also increase, and if W keeps on decreasing, my energy per length would also will proportionally decrease. Okay, so from the looking at the expression itself, you can, if you don't remember this curve also, from the looking into the expression of energy and like a delay, you can find like whether the curve is, what would be the nature of the curve. Okay, so it is one way to remember it. Hope that's clear. Take a moment to understand what like whether you are satisfied with what the logic that I have given or not. Clear? Okay, then we can move forward. Okay, so the next question is, find the T propagation delay per unit length for a fan out of 4 inverter given resistor per unit R, like per unit W is given, CW is given, fan out 4 value is given, and row inverter is given as half. That is for folded technology, right? This row inversion is half for folded technology that we have looked into it in the lectures. Okay, now let us find it. We know the expression for T propagation delay per unit length is RC 1 plus row inverter by L by N, okay, plus R into CW by W plus RW C into W plus here plus RW CW to L by N. Now for this one to have the minimum value, I have to put the L by N as the minimum. I have to replace it with a minimum delay expression. Okay, here also, and I have to replace what? I have to replace the W also with the minimum delay expression. Correct? Therefore, And what are the expressions? We note them. L by L by n for minimum delay is how much? It is 0.4 fan out of 4 1 plus rho inverter divided by RW CW. Similarly, W mean expression we have seen also, like in the previous questions. I have derived it also for you. R into CW into RW into C. Correct? So my TPD by L expression for minimum delay condition gets reduced to root under RW CW RC, okay, root under 2 into 1 plus rho inverter plus 2. So if you solve, if you put these values here and here and solve it, you will get this expression of T propagation delay per unit length for minimum delay condition. Okay. So now we also know that fan out of 4 is equals to R into 5C. Why? Like it is the condition, right, that one inverter is feeding similar 4 inverters. This is fan out of 4 delay, and here if it is C, here also it would be C plus C plus C plus C, so it would be 4C here. So net C would be C plus 4C 5C. So fan out of 4 is equals to 5RC, right? Therefore RC would be equals to fan out of 4 by 5. Fan out of 4 is given as how much? 15 picosecond. So 15 picosecond by 5 would be 3 picosecond. Correct? So okay, now let us do this, the final calculation. Therefore T propagation delay by L for minimum delay condition, I will be substituting it here. Okay, all the values that are given. RW is given as how much? RW is given as 200 ohms per millimeter. CW is given as 0.2 pico. Pico means 10 to the power minus 12 per millimeter. Okay, into RC. RC we have found as 3 picosecond. 3 into 10 to the power minus 12. Okay, into root under 2 into 1 plus rho inverter is given as 0.5. So it is basically 2 into 1.5, that is root under 3, that is 1.732 plus 2. So 1.732 plus 2 is 3.732. Okay, so let us do it. So it would become how much? It would become around, per millimeter is per 10 to the power minus 3, so it would become 2 into 2, 12 into 10 to the power minus 12 plus 2 minus 1, this plus 2 minus 1, again minus 12 for this, minus 3 would be plus 6. So how much it is coming? Minus 12 10, okay, minus 12 24, minus 24 18, plus 18, so 24, so minus 10 plus 11 minus 23 plus 17. Okay, so it would be root under 12 into 10 to the power minus 17 into 2 plus root 3, that is 3.732. So let me, give me a minute, let me see how much it comes. 12 into 10 to the power minus 17. It is coming as 4.088 into 10 to the power minus 13. Okay, so sorry, it is not coming as this. It's coming as how much? 10 to the power minus 8 it is coming. And 10 to the power minus 8 can be written as 10 to the power minus 8 so I want to write it as pico. 10 to the power minus 4 divided by 10 to the power minus 4. Okay, so it would become, and if I take minus 1, it would become 40.88 picosecond per millimeter. Correct? So it would become 40.88 picosecond per millimeter. Correct, right? I hope that's clear. The propagation delay per unit length for the minimum delay condition is coming as 40.88 picosecond per millimeter. Okay, fine. I hope I hope it's clear to everyone, right? Just take a moment and check whether you understand it or not. Okay, if it's clear, we can move to the next part. The next question, next question. Okay, so the next question is, in question number 5, like in the previous question, what is the optimal inverter size W, inverter size W scaling factor for minimum delay? Fine. So in question number 5, what is the optimal inverter size W, the scaling factor for minimum delay given the switching resistance of unit inverter is 10 kilo ohm, the capacitance of unit inverter is given as 0.3 femtofarad. Fine. So let's look into it. Therefore, what are the things that are given to us? R is given as 10 kilo ohm, C is given as 0.3 femtofarads, and RW and CW we have from question number 5. RW is how much? 200 ohms per millimeter. CW is 0.2 picofarad per millimeter. 200 ohm per millimeter. CW is 0.2 picofarad per millimeter. Right? Okay. Now it's straightforward. Like I have written the expression for W min, I think here. See, I have written the expression for W min here. Okay. Therefore, from there we can directly write W min. W with minimum delay would be how much? It would be R into CW divided by RW into C. Correct? So it's simply 10 kilo into CW is how much? 0.2 picofarad per millimeter divided by Rw is 200 ohm per millimeter to C is 0.3 femto. Femto is 10 to the power minus 15 to minus 15. Correct? So I can simply cancel millimeter from here. So the remaining terms would be 10 to the 10 into 10 to the power 3, so 10 to the power 4 into 0.2, 10 to the power minus 12 divided by 200 into 0.3, 10 to the power minus 15, it will become plus 15 here. Okay, so fine. So it will be 10 to the power 3 minus 10 to the power 3. So it is basically 10 by 3. So it would be 10 to the power minus 12 plus 15 plus 1 plus 1. So it's plus 3 plus 5 to 10 to the power 5 by 3. So let me check how much it is coming. 10 to the power 5 divided by 3 is 182.574. Okay. So 182.57 is the correct answer. So clear? In this way, we can find optimal inverter size W min delay with minimum delay condition for minimum delay condition, and the value is coming as 182.57. Okay. Hope the calculation is clear. Any confusion, anyone? No, right? Okay, then we can move forward. Like once you have you understand how to derive these expressions and from where we are getting these expressions, then it's simply you have to plug the values, you have to put the values, and you will get the corresponding result for W mean or number of stages, whatever has been asked. Okay. Okay, then let us move to the next question. It has been asked what is the energy per length per bit of information with reference to question number 5 and question number 6. So they have asked what is the energy per length. So they basically asked me what is the energy per length per bit of information with reference to question number 5 and 6. Okay. So the total energy consumed would be, like we know the expression, it is 1.866 CW into VDD square. If repeaters were not present, it would have been simply CW VDD square. But as repeaters were present, it is consuming more 86.6%, 66% of energy per unit length due to the presence of repeaters, right? In case of minimum delay. So if it was not the case of minimum delay and it was half of that, then we would have got energy of how much? Half of that, 43.33, like, because in the previous questions we have seen that it follows a linear relation. Okay. So with repeaters, as mentioned, like as in our case, our energy per unit length would be 1.866 into CW into VDD square. So 1.866 CW is how much? CW is 0.2 picofarad per millimeter, 0.2 picofarad per millimeter to VDD square. For 65 nanometer technology, we know VDD is how much? It's 1 volt. Correct? So let me check how much the answer is coming. The answer is 0.866 into 0.2 minus 2 divided by 10 to the power minus 3. Okay, so the answer is sorry, it's minus 12, not minus 2. Okay, so the answer would be 3.732 into 10 to the power minus 10 second, or 373.2 picosecond is the answer. Sorry, so why picosecond? It is energy, right? So it would be how much? Not second, it would be just give me a minute. Have I done anything mistake? 1.866 CW 0.2 picofarad per millimeter it was. Okay, 1.866 into 0.2 into 10 to the power minus 12 divided by 10 to the power minus 3. Okay. Oh, correct. So it would be, it is how much? It is joule per second, joule per length is meter. So if I convert it into picojoules per millimeter, then it would become 3.732 10 to the power minus 12, so plus 2 into 10 to the power 2, correct? So 10 to the power 2 joule per meter, so it will become 3.732 picojoule per 10 to the power minus 2 into meter, and if I make it minus 3, there will be 10 to the minus 1 at the numerator also, so it will become 0.3732 picojoule per millimeter. 0.3732, this is the correct answer, 0.3732 picojoule per millimeter. Basically it was 10 to the power minus 2, so I included 1 10 to the power minus 1 here, and the numerator also I have included 1 10 to the power minus 1 here, to the power minus 1 here, so it has become 0.37 picojoule per millimeter. Okay. Is it clear? Sorry. Okay. Okay, then let us move to the next question. See, actually the next part of the question is discussed in the next week's lecture, but as he has given this question in this assignment, like in the previous year he has given this question in this week 8 assignment, so let me discuss with you in a way that you will understand it. Okay. So the question is, in a 65 nanometer technology node, lambda is given as 25 nanometer, f clock is given as 1 gigahertz, and it is mentioned that a chip is designed which consists of 50 into 10 to the power 6 logic gates. So number of logic gates is given as 50 into 10 to the power 6. Width is given as 12 lambda, and lambda is mentioned as 25 nanometer. Fine. And activity factor is called alpha, is given as 0.1. Okay. So activity factor for uh, logic gates is alpha. Okay. So let me call it alpha L for logic gates. Similarly, the number of gates used in memory. So memory gates are memory gates are given as, so let it is nm is given as 950 into 10 to the power 6. W is given as 4 lambda. Lambda remains same for technology, that is 25 nanometer. And activity factor for alpha for 65 for memory gates are given as 0.02. And Cg is given as 1 femtofarad per micrometer, and C diffusion is given as 0.8 femtofarad per micrometer. Clear? Fine. Okay. Now estimate the power dissipated by VDD for the chip. So you have to estimate the net power that has been dissipated with the given conditions. Okay. So we know power expression for power dissipated is how much? It is basically capacitance into VDD square. Okay. But if a system is operating at a frequency of f, if a system, say a sequential system is there which is operating at a frequency of f, so it is obvious that at say this is my clock frequency f, then, and you know in sequential circuit generally they work at rising edge or falling edge. Okay, so f is the frequency. So any number of changes, like any arbitrary changes, should not be captured. The changes that has occurred during this rising edge or the falling edge, whichever the my flip-flops are, during this edge only my change in input would be captured as change in the output, corresponding change in the output. Okay, so my net power would become and linearly proportional to the frequency f. So power becomes P equal to CL VDD square f. Now one more thing, in circuit there may be hundreds of inputs. Okay, but if you look into the truth table, it might happen that any number of changes in the input will not result in a change in the output. Only certain changes in the input would result in a change in the output. So this factor is captured by this parameter known as activity factor alpha. Okay, it defines that how many number of changes in input are actually captured as a change in the output. Okay, so my net power dissipation would also be a factor of alpha, because if I have made 100 transitions, it is not necessary that all the 100 transitions would lead to a change in the output. Basically this is my dynamic power. And what is dynamic power and what is static power? Static power is the power that is dissipated when there are no changes in the circuit. If my say this was my input to an inverter and this is my output, so that when all the changes has happened, in this state the power dissipated are called as static power, and during this transition the power that is dissipated is termed as the dynamic power. So the expression of dynamic power becomes something such as CL VDD square into F into alpha. Okay, for one gate. And if there are n number of such gates, then the term n would also come into picture. For one gate, CL VDD square F alpha. For n such gates, it would be n FL CL VDD square. N F alpha CL VDD square. Okay. So now let us look into it. Let us find the value of this CL into, okay, let us find the value of CL first, CL and CM. Okay, so CL would be basically, of course NL would come into picture because n number of gates are present. Okay, into, for logic gate lambda is given as how much? It is given as 12 lambda. So 12 into lambda, so lambda would be, lambda is given as 25 nanometer, so 25 into 10 to the power minus 9, Okay, so this is basically my 12 lambda. Okay, and then CG and C diffusion would come into picture. So okay, so NL is how much? NL is given as number of logic gates is 5 into 10 to the power 6, 15 to 10 to the power 6. So 50 into 10 to the power 6, which is NL, into 12 lambda, which is 12 into 25 nanometer, right? 25 nanometer, 12 into 25 into 10 to the power minus 9. What else would come into picture? The capacitance. The capacitance is how much? Cg plus Cf. So 1 femtofarad plus 0.8 femtofarad per micrometer. So 1 plus 0.8 femtofarad, so 10 to the power minus 15, okay, per micrometer. So divided by 10 to the power minus 6. Correct? So if I solve it, it will come as, this is my basically capacitance. So if I solve it, let me print it. It's 50 into 10 to the power 6 into 12 into 25 into 10 to the power minus 9, okay, into 1.8 into 10 to the power minus 15, divided by 10 to the power minus 6. Okay, so it is coming as 2.7 into 10 to the power minus 8, that is 27 nanofarad. Okay, so this is my logic gate capacitance. Similarly, for the memory gate, the capacitance would come as n memory into lambda is 4 lambda into C. So n memory is given as how much? N memory is given as 950 into 10 to the power 6. 950 into 10 to the power 6. 4 lambda is given as 25 nanometer. It would remain same, 1.08, sorry, 1.8. Okay, into 10 to the power minus 15 divided by 10 to the power minus 6. So how much it would come? It would come, it is coming as 1.71 10 to the power minus 7 farad, that is 171 nanofarad. Fine. So now I know the value of CL and CM. Okay, now the dynamic power or the switching power would be sum of the power dissipated due to the logic elements plus sum of the power dissipated due to memory elements. Correct? So it would become alpha LCL plus alpha MCM space, okay, into equals into F into VDD square. Correct? See, the N is also taken care here, the alpha is also taken care, F is also taken care, VDD square is also taken care, C is also taken care, right? Actually, in the capacitance only, CL only, the N has been included. Okay. So let us see what is the switching power that is coming. So alpha L is how much? Alpha L is given as 0.1. Okay. So 0.1 into CL. CL is 27 nano plus alpha M is given as 0.02, I think. 0.02, yes, 0.02 into cm is 171 nano, into f is given as 1 giga, so kilo mega giga, giga is 10 to the power 9, correct, 10 to the power 9 into VDD square, VDD is 1 for 60 nanometer technology. So how much it is coming? It is coming as 2.7 nano. So 2.7 plus 171 into 2 is 342. So 3.42 nano will come outside, 10 to the power minus 9, 10 to the power 9. So it is coming as 356.12. Watt. So the answer is 6.12 watt. Hope it's understandable to you. Look at it once, whether you're understanding or not. Sorry. Check it once, whether you are understanding the point or not. How it is coming, what it is coming. Sorry. Clear? Any confusion? Any question? Yes, good evening. Oh, okay. See, CL and CM, what I did. See, first of all, CL and CM. So basically, width is given as 12 lambda or 4 lambda. Okay, 12 lambda is given for CWL and WM is given as 4 lambda. Okay, so basically, and we have been given CG and C diffusion. Okay, so my net CL and CM would be, say CL would be total number of gates that are available. Okay, logic gates were available, say 15 to 10 to the power 6 logic gates were available. Okay, so it would be NL, that is 15 to 10 to the power 6 multiplied by uh, 12 lambda. Okay, multiplied by 12 lambda multiplied by CG plus C diffusion. Okay, because in each of the gate, CG and C diffusion have to come into picture, so it would be NL into 12 lambda into CG plus C diffusion. Okay, the cumulative CG and C diffusion is given to us, so we don't need to find that what will be the effect of it. So CG and C diffusion we are taking that for each 1 lambda, CG plus C diffusion will be the capacitance. So for 12 lambda it would be 12 lambda into CG plus C diffusion. Okay, so this is my net capacitance for one gate, and multiplied by NL is the capacitance for NL number of gates. So CL is coming as how much? 50 into 10 to the power 6 into 12 into lambda is coming as 25 nanometer, correct. CG is coming as 1 and C diffusion is coming as 0.8 femto, so 10 to the power minus 5 per micrometer. Yes, they have given the lambda value. Lambda is given as 25 nanometer. See, actually, in the like current day technology nodes, you cannot directly say that whether like you cannot directly relate this lambda channel length. These things you cannot directly relate from the technology node name. Say, for example, you might be hearing these terms that 7 nanometer technology is present, 5 nanometer, 3 nanometer, TSMC. So, do you think the lambda is less than 3 nanometer here? See, like I think I told in previous classes also, say for 3 nanometer technology, okay, if my lambda is 1 nanometer or 2 nanometer, okay, so you have heard about this term tunneling, right? Electron tunneling. So tunneling becomes a like major phenomena around 5 nanometer technology, 5 nanometer length. Okay, so below 5 nanometer you will have FN tunneling. Below 3 nanometer you would have direct tunneling. So you won't be able to control the gates. Okay, they would be out of control. They would be always on because electron would tunnel from drain to source. So when we are talking about these technologies, we cannot directly say that the lambda is half of it. Okay, so the names have become such some kind of preposterous naming. Okay, so you cannot directly relate them. It depends on the technology node. It is defined in the compact model. It defines in the PDK that what would be my lambda and all. What would be the design rules. Everything is defined, but you cannot directly say. In the previous day technologies, you could have said that half of it channel length is basically lambda, but it is still it does like it is no longer a valid argument. Okay, so for 180 nanometer, you can say 180 nanometer or maybe even 135 nanometer, you can say. But below that, it is somewhere near 1 by 2 lambda, even at 65 nanometer, 45 nanometer technology. But around 20 nanometer or 16 nanometer, 22 nanometer or below, like this name does not make any sense. Okay, actually for 3 nanometer, lambda is something around 16 nanometer or 18 nanometer or 20 nanometer. So to answer your question, lambda you cannot directly say it is half of that. Is it clear? Nazma, right? Hello. Am I audible, guys? I think she has lost the connection. No problem. Okay. If that's clear, we can move forward to the next question. Fine. Let us look into the last question for class. So it has been mentioned, find the decontamination delay for the signal propagating in wire A, neglecting the parasitics of the inverter and the wire's resistance. Okay, so we have to find the contamination delay. Okay, so contamination delay and propagation delay, as I have already mentioned in the first question, propagation delay means the worst case delay, and contamination delay means my best case delay. Correct? And as I have already mentioned in question number 1 also, reiterate let me reiterate it for you that say we have two wires here. Okay, so if the driver of the aggressor is changing its state and there is no driver in the second stage, the capacitance that it needs to charge is basically Ca plus C adjacent, right? So it would be my net C would be Ca plus C adjacent. And if the driver, if the aggressor and the victim are charging in the same direction, are changing in the same direction, so this del V across this C adjacent would be 0, right? So my net capacitance that this aggressor circuit needs to charge is only Ca. And if the aggressor circuit and the victim circuit are changing state in the opposite direction, then the del V encounter would be double the value of the C adjacent, right? Because it is changing from low to high, it is changing from high to low. So the effect on the C adjacent would be like, it will be double. So then it has to charge, this circuit needs to charge C adjacent plus 2 into CA plus 2 into C adjacent amount of capacitance, correct? And as in this condition, it has to charge the least amount of capacitance. This driver circuit needs to charge the least amount of capacitance, so it will give me the best case of delay, okay, the smallest amount of delay. So this would leads to my contamination delay, and as this is the highest amount of capacitance, it needs to uh, charge the highest amount of capacitance, so the delay in charging this capacitance would be the highest. So this would give me the worst case delay, sorry, this would give me the worst case delay or propagation delay, and this would give me the best case delay or contamination delay, correct? Therefore the expression of contamination delay would be simply R effective into CA, correct? If it was propagation delay, it would have been how much? R effective into CA plus 2CA adjacent. But as it is contamination delay, it is simply R effective into this capacitance CA. Okay. So R effective is given as how much? R effective is given as 1 kilo ohm, and L is given as 1 millimeter. CA is given as how much? CA is given as 80 femtofarad per micrometer. Therefore decontamination delay would be R effective, that is 1 kilo, into CA. CA is 80 into femto, that is minus 50 per micrometer. So for 1 micrometer it is 80 femtofarad. So for 1 millimeter it would be 80 into 10 to the power minus 15 by 10 to the power minus 6 into 1 millimeter, that is 10 to the power minus 3. So this one and this one would cancel. Okay, so it would come 80 into 10 to the power minus 9. So it would come as 80 nanosecond, correct? Here it is given as 80 picosecond, it would be 80 nanosecond. The range is given wrong here. Okay, so the answer is, like even in the question number 1 it was, the range was not correct, it would have been microsecond instead of nanosecond. Here it would be nanosecond instead of picosecond. The question number 1 also, if you remember, it was microsecond instead of nanosecond. Here it is coming nanosecond instead of picosecond, correct? Any confusion? Anyone? Okay, see. See. See, here is the C adjacent capacitance. Okay. So it is my aggressor circuit. This is my aggressor circuit. Okay. So when it is making a change, say it is going from low to high. So this from 0 to VDD. So this VDD needs to charge how many capacitances? 2 capacitances, right? It needs to charge this CA. So this needs to charge this CA. So this CA it needs to charge, and it needs to also charge this capacitance C adjacent. Okay. So it is charging 2 capacitances. So the net capacitance it needs to charge is CA plus C adjacent. Okay, and I have considered it is not been driven by anything, it is a floating node. Okay, in this case. Now if it is driven by another driver and they both are changing in the same direction, so the voltage across this capacitance, say it is this voltage, due to this change, as this is a symmetric circuit, you can see it is completely symmetric, right hand side and left hand side they are symmetric. Okay, So the voltage that would be developed here, say Vx, due to this changing voltage, and the voltage that would be developed here, say Vy, due to this changing voltage, they would be similar. As voltage developed across these two terminals are similar, so the voltage difference Vxy would be 0, because Vx and Vy are 0. So like it is more appropriate to say V adjacent, the voltage across this C adjacent would be Vx minus Vy, which would be equals to 0. So now this driver circuit, aggressor circuit, needs to charge only this capacitor CA. So the capacitor that it needs to charge is only CA, and this is the condition for contamination delay. Okay, like we have done. Now let us take a condition when the aggressor circuit is changing direction and the victim driver is also changing direction, but they are changing direction in the opposite way. Okay. Now if initially, if this voltage is Vx and this voltage is Vy, initially what if it was 0.2 volt, this was also 0.2 volt, because it is going from 0 to 2, and it is going from it was also going from 0 to 2. Now if Vx is 0.2 volt, how much would be Vy? Vy would be something around 1 minus 0.2 volt, that is 0.8 volt. Okay. In the first case, if it was 0.2 volt, it was 0, so it would have been 0.2, like in the first case, in this case it would have been Vxy would be how much? 0.2 minus 0 equals to 0.2. Second case, it was 0.2 minus 0.20. I'm giving an example. Okay, these are not hard and fast values. Here it would be how much? 0.2. It would be 0.2 minus 0.8, so around 0.6. Okay, the values that I have chosen are not correct, but the concept is here this Vx and Vi would be in opposite polarity. Okay, if I consider it 0.2, I might consider it as minus 0.2, not negative in the sense, but this voltage is in the reverse direction. It was charging, so this Vx was positive, it is discharging, so it would be something negative. It would be opposing this aggressor circuit. Okay, initially the Vx and Vy were such that the potential difference across this was got cancelled, but now the potential difference would be such that they would cumulatively sum of the effect, and the net capacitance that I would need to charge would be double the initial value. And why double? The voltage, if it was say with the reference, if it was 0.2 volt more than the reference, now it has become 0.2 volt less than the reference. Okay, so now I have to charge twice the amount of capacitance, or I should not say twice the amount of capacitance, it is more appropriate to say the voltage that I need to store is twice. Okay, not even the voltage, the charge that is needed to be stored to achieve the same voltage is twice. So I can simply simplify this in the terms of saying that the capacitance that I need to charge is twice. Does it make sense? The work done by this aggressor circuit to discharge it would be now twice of this condition. Okay, that's why I am saying the capacitance would be Ca plus 2C adjacent, and this is the worst case, so it is giving me the propagation delay because it has got the highest amount of capacitance. Is it clear from where we are getting this? Hope no confusion is there. Okay, as now this aggressor circuit has to do more amount of work, and this is not aiding it, it is repelling it. So as the work done is more, I am saying that now it has to charge twice the amount of capacitance. Okay, so the C adjacent is replaced as 2 into C adjacent. Okay, so from here I am getting, and did you get the did you understand the from where I am getting the CL from the previous discussion? Was that clear? Okay, okay, so see, it was okay, fine. Y- yes, yes, okay, good. Anyone else, any question? So the questions for today's class is over. So if you guys have any question, you can ask me. I'd be happy to discuss it with you. Any confusion within these questions? See, the question number 10 was regarding contamination delay, and question number 1 was regarding propagation delay. Okay, so same here. What? Yes, here I have used 2C adjacent because I am calculating the contamination propagation delay. In the last one, I have used uh, contamination delay, so I have used all this formula. This is R effective into CA. I have not included this 2C adjacent. I have not included. Simple. Okay. Uh, why? Okay. State if the statement is true or false. C2 MOS register is insensitive to overlap. Hello. Okay. So state if the statement is true or false. C2 MOS. Okay. Register is insensitive to overlap as long as rise and fall times of the clock are sufficiently small. Why the option 4 is correct? C2 MOS register is insensitive to overlap as long as rise and fall times of the clock edges are sufficiently small. Okay. Actually, I don't have access to the previous week's notes as of now, so even I forgot what was C2 MOS circuit. Just give me a minute. Okay, let me do one thing, Uttara. Just ping me in the mail once. I'm giving you my mail ID. Just ping me in the mail once. Once I get free, I'll get back to you with the answer. Okay. I have to check it once. I don't remember exactly what was happening. Ping me in the mail once. Yeah, I have shared the mail ID. Okay. Anything else? Yes. Okay. Actually, I don't have access to. I'm sitting in my lab right now, so I don't have access to that right now. So, but still, okay. Tell me what it is. Okay. Acha, 2:1. Okay. Yes, tell. Okay. I don't remember the formulas actually. I have to see the notes that I have made. Just do one thing with the questions that you have regarding the previous assignment. Just ping me in the mail once. I'll get back to you with the answers within tomorrow. Okay? Because I don't. I'm sitting in my lab right now. So yes. Okay. 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 Yes. 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 Like how much I could recall it was if instead of 1 is to 1, if it was 2 is to 1, for 1 is to 1 we are already calculating, right? For 2 is to 1 we were considering some extra terms that we have added. Yes. Okay, you mail me the question. I will look into it. I'll help you to solve it. Okay. Okay. Okay, understand. Okay. 4 is to 1, NOR gate you are saying? NAND. Okay, this was also NAND gate, right? NOR gate, right? Okay. I think NOR gate it was pretty standard. I also discussed in the previous class, right? Okay, no issues. You send me the question once, I'll check it. I'll get back to you on this. Okay, and it won't be that difficult. And if you find that the answers that have been given by them is not matching, just mail the professor or mail NPTEL team once. Okay, there should be some point of contact mail given to you, and if it is not there, you can simply go to professor's website, Professor Mathavrao's website, and you can get his mail ID, and you can simply mail him that, sir, these are the problems that we are facing, and the answer is not matching. Can you kindly say why you have given the answer as such? So he's a professor in Triple IT Bangalore, right? So let me check right now. He's a professor in Triple IT Bangalore. So if you go to the his every professor has his own website. Okay. So if you go into the website, you will get the details of the mail IDs and all. It is a norm to maintain the website for every faculties, and nowadays even PhD scholars have to maintain their websites. Okay, so where we generally keep track of all the research we are doing, all the publications and all the contact details and all, so that everyone can contact us. So we have to maintain it, and professors have to must they have to must like it is must for them. So you can go and mail him from there, or you can mail the NPTEL team as well, that there are some issues, can you kindly clarify this point. Okay, anything else? I Okay, I have shared you the mail ID. Kindly mail me once regarding the problem. Okay, in the comment section, I think you joined late, so okay, let me share it again with you. Yes, yes, sure. So, okay, so any more further questions, anyone? So if there are no further questions, we can call it a day. Okay, so see you next week in week 9's discussion session, and in the meantime, I'll just ping me once. I'll get back to you regarding your queries. Okay, thank you everyone.